Hi, I am Ciro Donalek, and in this module, I'll be walking you through one of the most exciting data mining tasks, clustering. We'll cover terminology, definition, and we'll see in more details some of the models, like k-means and self-organizing maps. As the previous ones, this is a really broad subject, so the purpose of these lectures is to give you insights on all the problematics and also help you choosing the right models and the right parameters to set to apply in your analysis. Now, the difference between clustering and classification may not seem great at first, but let's remember that classification is a form of supervised learning, while clustering is the most common unsupervised task. So the model is not provided with the correct results during the training. According to the cluster hypothesis, objects in the same cluster behave similarly, meaning that points in the same cluster are likely to be of the same type, sharing, for example, some common statistical characteristics. With the clustering, basically, we want to find natural groupings among objects. So let's start with some examples. So, suppose this is our data set, Simpson characters. How would you divide them in clusters? And be careful, because the notion of cluster can be ambiguous, as we see shortly. So we can divide them by gender, females and males, but also we could divide them by their role in the series, like Simpson family members versus school employees. So these are two different but plausible clusters for this dataset. Now, let's see another example. We have this set of points. How many clusters do you see? I'm pretty sure most of you would say just two clusters, because there are two groups of points that look really well separated. But some may see 4 clusters, or even 6 little clusters, as shown in the figure. From these examples, we can derive that clustering is indeed subjective, but in a few moments we will also see some measures that we can use in evaluating the quality of a clustering. Now, let's first discuss why we need clustering. For example, organizing data into clusters may show the internal data structure, and that's one of the goals in gene clustering. Or we can use partition to achieve a goal, like in marketing segmentation, where the goal is to discover distinct groups in the customer bases and then use this knowledge to develop a targeted advertisement, for example. Another task is to find anomalies or outliers that could be just measurement errors or cool rare objects. Outliers can be defined as in the picture, where we can see 2 distinct clusters and an object that seem to not belong to any of the clusters. Now, and clustering, of course, has many applications in almost all scientific fields, like astronomy, visualization, and so on. Now, let's give a more formal definition. Given a set of features vectors D, a desired number of cluster K, an objective function G, we want to assign each feature vector to one cluster in order to minimize or maximize, in some cases, the objective function. The objective function is often defined in terms of similarity or distances between samples or clusters. Now, we need to answer some basic questions, like what does similar mean, how we can define a good partition, how to measure the quality, and so on. So let's start in how to evaluate clusters. We can use two types of criteria, internal criteria and external ones. Internal criteria are based on the distances between points in clusters and the distances between the clusters. And we'll see them in a moment because there are many ways to compute those. External criteria can use direct evaluation and the gold standard when available. Direct evaluation means that experts or users can manually check the clusters and apply them in the domain of interest. This is, of course, the most direct evaluation, but it can be also very time-consuming or unfeasible when we deal with huge amounts of data. So it's unfeasible to look one by one. Now, an alternative is to use a labeled subset created by experts where the classes are known and compute some measures on those. Now, let's start with the internal measures. They can be divided in two big classes. Intra-cluster distances, that are the distances between the points belonging to the same cluster, and the intra-cluster distances, that are the distances between clusters, as shown in the figure. Now, typical objective functions in clustering aim to obtain a low intra-cluster distance and a high intercluster similarity. So we want all the points in a cluster close together and the cluster as distant as possible. Now, we'll see some of these distances later when we talk about hierarchical clustering, because they are also used to merge clusters. Now, keep in mind anyway that good scores on internal criterion do not necessarily translate in good effectiveness in an application. Additionally, this evaluation may be biased towards algorithms that use the same criteria to build the clusters. For example, k-means, that we'll see in the next video, naturally optimize object distances, and the distance-based internal criterion will likely overrate the results of this type of clustering. So internal evaluation are best suited to get some insights, but we cannot imply that one algorithm produces more valid results than another just based on the internal criteria. Now, external measures instead use a subset of labeled samples when this is available. Keep in mind that the learning is still unsupervised because the results are evaluated based on this data that is not used for the actual clustering. And so this data is often created by human experts, and the most used measures are purity, normalized mutual information, rand index, F measures, or Jaccard measures. Let's start with purity. Purity can be seen as the equivalent of accuracy in classification. So we assign each cluster to the class which is most frequent and measure the purity by counting the number of correctly assigned samples per class. So high purity is easy to achieve when the number of clusters is large. In particular, purity is 1 if each sample gets its own cluster, and that's not something we actually want. For this reason, we cannot use purity to trade off the quality of the clustering against the number of classes. To do so, we need other measures. Now, this is an example of how purity is computed. We have 3 different classes, cross, circles, and diamonds. And let's suppose our algorithm finds 3 clusters, as in the figure. So the first one is assigned to cross, because we have 5 crosses and just 1 circle. The second is assigned to circle, and the third is assigned to diamonds. The overall purity is 71%, and of course the first cluster is the one that looks the more reliable. So we have some sort of purity also cluster-based. Now, the normalized mutual information, or NMI, measures the amount of information by which our knowledge about the classes increases when we are told what the clusters are. But this measure has the same problem as purity, because don't penalize large cardinalities. So while we usually want to follow the rule that few clusters are better, of course, other things being equal. Now, let's see other two measures. The RAND index measures the percentage of decisions that are correct. It is defined as the sum of the true positive plus the true negative over the total number of elements. So in this formula, false positive and false negatives have the same weight. But as we have also seen in classification, we may want to penalize one of the two. So we can introduce weights and use the F measure. So, and if you see the formula of the F measures, there is a beta parameters, and if we want to penalize the false negative, it's sufficient to put beta greater than 1. Now, let's now see how many different types of clustering there are. We can say that there are 4 main sets. And roughly speaking, in hierarchical clustering, we want to find a successive cluster using previously established ones, while in partitional clustering, data samples are divided in non-overlapping clusters. Then, in model-based clustering, we assume that the data are generated by a model, and we try to recover the original model from the data. The model that we recover from the data then defines the cluster and the assignment of samples to the cluster. So, for example, in the left figure, we have 3 clusters of points generated with a Gaussian distribution, and we can see that the EM algorithm works well, recovering all 3 of them. While in the density-based approach, like the one on the right, clusters are defined as areas of higher density than the remainder of the dataset. Objects in these sparse areas are usually considered to be noise and border points. Now, let's talk more about hierarchical clustering. In hierarchical clustering, we try to find subsequent clusters using previously established ones, like I said before. Now, of course, we cannot do an exhaustive search based on all possible combination because it would be computationally unfeasible. That's why we need to use some heuristics, and we can further divide the hierarchical cluster algorithms in agglomerative or bottom-up and divisive or top-down. In a bottom-up approach, we start with each element in a separate cluster and then merge them accordingly to a given property. On the contrary, with the top-down approach, we start with all the points in just one cluster and then start dividing them. Let's see with the 2 example how this works. So suppose we have 6 points distributed as in the left figure, as in the right figure. So black numbers are the points, and in red the clusters created. In a bottom-up approach, we start with the 4 clusters, 1 and 3, 2 and 5, and 4 and 6 have their own clusters, and then we can start combine them. No, hierarchical clustering, of course, has some pros and some cons. In hierarchical clustering, one of the pros is that we don't need to specify in advance the number of clusters, and we can later decide where to cut in order to have the desired number of clusters. It's also intuitive because we are also used to think this way. Unfortunately, they do not scale well, like any heuristic algorithms, local optima can be a problem. Now, so far, we have talked about distances between clusters and ways to merge them. Now we can see in detail some alternatives. Single link is defined as the smallest distance between an element in one cluster and an element in the other. This is a local measure, since we pay attention only in the area where the two clusters are close to each other. So other more distant parts of the clusters are not taken into account. So we don't really pay attention to the shape of the cluster when we use this distance. Now, complete link clustering takes into account the largest distance between an element in one cluster and an element in the other. Basically, we measure the similarity of two clusters as the similarity of their most dissimilar members. Now, this criterion is not local because the entire structure of the clustering can influence the decisions. And so this method works better for compact clusters with small diameters over long clusters. But it is also very sensitive to outliers. For example, just one sample far from the center can increase the diameters of candidate merge clusters and completely change the final clustering. Another method that probably is the most commonly used is the average link, and is defined as the average distance between an element in one cluster and an element in the other. Basically, the cluster quality is based on all similarities between samples, and so we can avoid all the pitfalls of the single link and complete link criteria, which equate cluster similarity with the similarity of a single pair of samples. Other measures involve centroid and medoids, and we'll see when we talk about k-means. Now, we talked about similarity, and in general, similarity measures are functions that quantify the similarity between two objects, and they are based on distance metrics. Now, let's see some distance measures and when we should use them. Euclidean distances are probably the most commonly used and produce a kind of sphere-shaped clusters. They are often used in optimization problems, and especially the squared Euclidean distance, even if it's not really a metric because it doesn't satisfy the triangle inequality. Now, the taxicab geometry is a form of geometry in which the usual Euclidean distance is replaced by a new metric in which the distance between 2 points is the sum of the absolute differences of their Cartesian coordinates, and they produce a sort of diamond-shaped clusters. Cosine similarity is another distance commonly used in information retrieval. Basically, cosine similarity generates a metric that shows how related are two samples by looking at the angle instead of the magnitude. For example, in text mining, gives a useful measure of how similar two documents are likely to be in terms of their subject matter. For example, like in the figure, for similar scores, vectors are in the same direction, forming an angle near to 0 degree. The Malanobis distance is a measure of the distance between a point and a distribution. And in the previous video, we have also seen some other distances that can be used for text or binary data, like the Hamming distance. Now, we have talked about hierarchical clustering. Let's now briefly introduce partitional clustering that you will see more details when we speak about k-means. In partitional clustering, we need to specify the number of desired clusters k, even giving it in input because we know what to expect, or trying multiple ones and determining the best using some measure. In partitional clustering, each instance is placed in one of the clusters, and we can have hard and soft clustering. In hard clustering, each sample is a member of one cluster exactly. An alternative definition of hard clustering is that a sample can be a full member of more than one cluster, but a full member. So it's like a sort of crispy classification. 0, 1, belong to a cluster, not belong to a cluster. In soft cluster, each sample has instead a degree of membership for each cluster. Some researchers also distinguish between exhaustive clustering that assign each sample to a cluster and non-exhaustive clustering when we can have some samples that don't belong to any of the clusters. And that can be useful in, for example, for outlier detection. Now, in summary, in this video, we have talked about the different types of clustering, how to choose the right model, metrics and objective function depending on our problem. Then we have introduced the hard and soft clustering that can be related with the crispy probabilistic classification for supervised algorithm. And we have also seen the difference between the exhaustive and non-exhaustive clusters. Now, in the next two lectures, we'll see some models in more details.